Let's open this video with a couple of examples. Y'all, sigma is a number theoretic function that sums the divisors. So let's just pick 10 because it's an easy compute. Now this says to sum up all the divisors of 10, which include 10, and of course always 1. So 1 is always kind of a boring element here, and then 2 plus 5 plus 10. This is sigma. I think it's lowercase or uppercase, I'm not sure. But so that's equal to 18. Okay, that's the sum. Now I've used the lowercase d for this thing here, but the tau, let me see if I can make a half-hearted attempt at doing a tau. Okay, I used to use lowercase d for this, and a lot of older number theory books did also, but it just counts them. Okay, so tau at 10 counts the number of divisors, including the number itself, and so we can count them here. There's 1, 2, 3, 4. So that's equal to 4. Now what we have right here is an equation that involves both of them. Okay, now and a lot of you who are familiar with this will know that there's going to be at most one answer here, and you'll see why as this goes along. Now, tau at n for all prime n is always equal to 2, and that's literally how a prime number is defined. For example, tau at 13 equals 2. And again, folks, that's how a prime number is defined, and it has 2 positive divisors, 1 in itself. Okay. Now, also something else that's quite useful. Notice that tau at, I'm probably overdoing the tau symbol there. Tau at, or excuse me, sigma. Let me erase this. Sigma at 13 is just equal to 13 plus 1. I'll write that down for emphasis. 13 plus 1 equals 14. So you see what we can conclude right here, folks, is if you replace this with just a general p, the answer is always going to be 2 by definition. If you replace this with p, the answer is always going to be p plus 1. Right there, equals to p plus 1. So it's pretty simple to operate on these equations because these two formulas are so simple. Again, sigma at p is always p plus 1. Tau at p is always 2. Okay, so let's get busy solving this thing, see if we have any solutions. Now, so I put the 2 right here, substitute right here. That's equal to 32, folks. And so this results in sigma of n being 218. Now notice that that would mean if n were prime, again, I'm saying if n is prime, sigma at n is equal to n plus 1. And again, this is conditional here. If n is prime, and this is true, so we would have to consider n equals 17, right? It's either prime or it's not prime, right? So 217. Y'all, there's a divisibility rule for 7, but this is pretty easy to see that this is equal to 7 times 31, right? So the only possible candidate for a solution would be 217, and it's semi-prime. 7 times 31 is 217. So the answer is no solutions. No prime solutions, all right? And I'll just do this solutions abbreviated. My abbreviation probably. All right. And by the way, folks, if you're interested, there's a divisibility test for larger numbers. Notice that if you take the last digit here, which happens to be 7, all right, multiply it by 2 and subtract it from the rest, you would get 7, which of course is divisible by 7. In general, if you take the last digit and subtract it from double it, subtract it from what remains, if whatever is left is a multiple of 7, then the entire integer is a multiple of 7. You don't need to use that test here because it's clear that 7 times 31 means that this is a composite number. Okay, so the answer to the question is how many? We can put none. No solutions. And again, my claims lack rigor, but the prime, all of this would keep growing, and you know what I mean? This has to be the answer because of the nature of this constant. It's very, very restrictive, and there couldn't be any other primes because all primes enjoy this property of 32, right? I mean, 2 and then 2 to the 5th would give you 32, right? 2 to the 5th is always going to be 32 right here, right? And so that doesn't change for any prime, no matter what its size is, okay? So then some of the divisors are just going to keep getting bigger and bigger and bigger with larger and larger numbers. Generally speaking, that's not completely true, but I'm holding to my claim that there are no prime solutions here. And again, a little bit of hand waving as usual. Okay, thanks for viewing.